In the photoelectric effect, you have a piece of metal surface, and there are electrons in that metal, and we can eject these electrons by shining light, but only light that has enough energy will eject these electrons. We call that threshold energy, right? A light with a certain amount of frequency. Anything less than that energy, the electrons won't eject. For this metal, for electrons to eject, requires 6.889 times 10 to the negative 19 joules. That's known as the work function, also the threshold energy, you can say. So we'll just label that E0 or E naught. And any extra energy that that incoming light had or has is going to get transferred into the kinetic energy of that electron. Now, that makes sense, right? So we'll write that up here. The energy of the light, or the photon here, the incoming light, is going to equal, part of that's going to go into the threshold energy, the energy required to dislodge one of these electrons, and then any extra is going to go into the kinetic energy of that electron. Right, so to answer the first part, let me change the color up a little bit here. This one, part number one, I guess. What is the energy of the incident light, the incoming light? Well, that's going to be just the two numbers given. I'm just going to add them up. All right, so here we go with 6.889 times 10 to the negative 19 plus 1.266 times 10 to the negative 18. All right, and our answer is going to be 1.955. Times 10 to the negative 18. That was the bigger number, joules. All right, the sig figs are right too, because if you align these up, you can make this one bigger by moving the decimal over, and then this one turns out to be, this one has more precision, so our answer needs 3 decimal places if it's 10 to the negative 18. Anyway, sig fig's not a big deal here. So there's the energy of the photon. Now we can use that to get, let's say this is part 2, the frequency and the wavelength. So we have a couple formulas we can use. We can use this one here, where the energy, let's write this one we know, right? So we can get the frequency using E equals Planck's constant times frequency. Let's rearrange that. Divide through by Planck's constant, and you get energy over Planck's constant is frequency. All right, so energy is up here. All right, I'll just write that again. 1.955 times 10 to the negative 18. Right, and then Planck's constant is 6.626 times 10 to the negative 34 joules seconds. All right, joules are going to cancel out, and we'll be left with per second. Let's go back to our calculator. And that number is already stored there, so that's my energy. I'm just going to divide it by Planck's constant, which is 6.626 times 10 to the negative 34. All right, now our sig figs is, no, sig figs matters, not placeholders, because we're dividing. And so 2.950 times 10 to the 15th, I think it was. And you can go with per second, or you can go with hertz. All right, so there's an answer to frequency. Let's make sure it's times 10 to the 15. Yep. Right, now the wavelength, we can use this equation. Speed of light is equal to the frequency times the wavelength. There's other equations you can use, but this is just let's go this way. Right, so divide through by frequency and you get wavelength is equal to speed of light over frequency. Speed of light is 2.998 times 10 to the 8 meters per second. And frequency, we just solve for that. (15 per second). So these are going to cancel out. We'll be left with meters, which is going to be a SI unit for length, wavelength. All right. So the speed of light is 2.998 times 10 to the 8 divided by that number we got earlier, still stored in my calculator. All right, so it's going to be 1.016 times 10 to the negative 7, I think it is. Okay. Meters.